Hello class and welcome back to AP Computer Science Principles. I am Professor Cunningham and today we are actually going to go through Khan Academy's article on converting analog data to binary instead of me just suggesting you check it out on your own, because there's a lot of really good information here that I think you're going to benefit from. So without further ado, let's go ahead and get started. The real world is analog, a continuous stream of varying data. Just look around you. Beyond your computer or your phone, there's an infinite amount of visual information. If you zoom in to one part of your visual field, you can notice more and more details. Now sing a little song to yourself. That's an infinite stream of audio information. Your voice is constantly changing in big and little ways, microsecond by microsecond. Analog data is infinitely detailed. Computers can only store digital data, finite data, in a binary representation. So again, infinite means there's no end, and finite means that no matter how much it can hold, there is an end to it. So how can we capture the wondrous analog world of our senses and convert it into digital data? We can use a process of sampling, quantization, and binary encoding. Those of you who are taking a class, this is a great time to get your notebook out and write these down, because again, this vocabulary is going to be pretty important. Let's start with a simple analog signal, a waveform representing a sound. There it is. All analog signals are continuous, both in the time domain, which is the x-axis, and the amplitude domain, which is the y-axis. Now, let's go ahead and double-check those definitions as well. Time is exactly what you think it is. It goes from, it looks like 0 to 330. They didn't give us a unit here, but that's time, whereas the up and down looks like, I think V stands for volts, and it's just the distance from that curve to 0. So the amplitude is how high up or how far down this curve goes. That means there is a precise value for every possible value of time, even as specific as 1.2345 seconds, or even more specific than that. And that value may be as precise as that many volts. This curve is analog for a reason that I try to explain to my algebra students every year, and that's that this curve is basically an infinite number of points, all crammed together, infinitely close to each other. No matter how far I zoom in, I will never find space between any of these points. And I could put in any time as specific as I want, and I can get out a voltage from that graph, assuming I've got, say, the equation of it. So it seems like we're stuck. How do we deal with this? How do I take this analog curve, which can't be digitized, and somehow digitize it anyway? We do it through a system called sampling. What sampling is a process where we take a sample at regular time intervals. This step reduces the continuous time domain into a series of discrete intervals. So for example, in this particular curve, we have time going from 0 to 330 milliseconds, that's the unit. And we could take a sample every 30 milliseconds. So as you can see, we start with one at time 0, then there will be one at time 30, 60, 90, all the way up to 330 milliseconds. That gives us 12 samples, including the ones at both ends, of the signal between 0 and 330 milliseconds. Now, I want you to take a look at that graph for a moment and imagine that you can't see the yellow line, you only see the orange points. Do those orange points by themselves look like a reasonable approximation of what that yellow curve looks like? So now what we can do is we can take those 12 points, we can get the x and y coordinates of them, and then we can convert those coordinates into binary. However, you will notice that the y values are only as precise as the computer can store. Numbers stored in computers are not infinitely accurate. They may be rounded off. I see a lot of numbers up there that are probably rounded off, which does mean, once again, we are approximating real life. We are not duplicating real life. Is 12 samples enough? Play around with the sampling interval in the interactive below and observe the effect on choosing different intervals. I will, of course, put a link to this article in the description of this video, so please feel free to go in and mess around with it on your own. Now let's see what happens if I take the sampling interval and make it bigger. As you can see, what that's done is it's widened the space between the points, which means there are fewer points. And in fact, I would say that this is a very bad representation of that curve, because from the first to the second point, it looks like it's just going down, whereas it's supposed to go way up and then down. So when you have a sampling interval that's too long, you really lose out on a lot of the detail. If I make the sampling interval really short, well, now you can see, once again, if you pretend that you can't actually see the yellow curve, you can only see the orange dots, that's pretty close to the actual curve if you were just looking at those points. The shorter your sample interval, the more samples you have, and the bigger file you've got, but also the more detail you can manage. The inverse of the sampling interval is called the sampling rate, the number of samples in a second or other unit of time. For example, a sampling interval of 30 milliseconds corresponds to a sampling rate of 33.33 samples per second. It's just inverting the fraction, and it's the difference between miles per hour or hours per mile. How many miles can you go in 1 hour versus how many hours does it take you to go 1 mile? They're connected, they're inverses, but you need to make sure you know which one you're working with at any given time. According to the Nyquist-Shannon sampling theorem, a sufficient sampling rate is anything larger than twice the highest frequency in the signal. The frequency is the number of cycles per second and measured in hertz, which I believe is cycles per second. If a signal has a maximum frequency of 500 hertz, a sufficient sampling rate is anything greater than 1000 hertz. A typical sampling rate for music recordings is 48 kilohertz, or 48,000 samples per second. Remember, kilo means 1,000, so that's 48,000 samples per second. That's a little over double the highest frequency that humans can hear, which is 20 kilohertz, or 20,000 hertz. If the audio only contains human speech, as is often the case for phone calls, a much smaller sampling rate of 8 kilohertz can be used, since 4 kilohertz is the highest frequency in most speech. This is why a phone call or a Zoom call has a lower sound quality than, for example, a podcast. Okay, quantization is a word that seems like it's going to be really confusing, but if you understood what we did before, where we took a continuous spectrum of time and chopped it up into individual pieces with nothing in between, then you'll understand quantization, because it's the exact same process, only for the amplitude, the y-axis, rather than time, the x-axis. It's the exact same process. In fact, back up here, when we were looking at x and y, we had to round off y, because once again, maybe that would be a decimal that would go on forever, and a computer can't deal with that, so it had to round. All quantization is rounding. For our simple signal, where amplitude varies from -100 to 100 volts, we can apply a quantization interval of 25 volts. So what we've got over here are all those orange dots from further up in the article. But now, instead of putting them exactly where they are, you'll notice that they've circled a point that is kind of the nearest 25 volts to the orange point. In fact, this is really a good visualization of what rounding is. They're taking each point and they are sort of scooting it a little bit so that it is on the nearest 25 volts to that point. Now the 12 points all have y values that are multiples of 25. So not only is it way simpler than those horrible decimals that we had up above, it's also going to take up a lot less space, because something like -75 is a whole lot easier to represent in binary than something like 74.45602 or whatever. Now the article asks, what's the best quantization interval? Play around with different quantization intervals below and observe how far the quantized points are from the sampled points. If I never hear the word quantization again, it'll be too soon. Anyway, as you can see, this is the same thing that we had before. If we increase the interval, it means that a lot of these points, look at those 4 down at almost -100. They all look like they're the same, even though those are 4 clearly different points. So the bigger the interval, the less accurate we're talking. So if I make the interval really small, now you can see that the purple circles, which are our final points, are almost perfectly overlapping those orange points. So remember, if you want your sound to be more lifelike, more realistic, you want to decrease both the sampling interval to get more points and the quantization interval to make sure that those points are as accurate as possible. Of course, doing this takes up more data, which is why high quality sound and video takes up so much more space on your hard drive than something a little bit lower quality. The ideal quantization interval depends on our use case and physical constraints. If there is enough space to represent thousands of different y values, then we can use a very small quantization interval. If there is limited space, we can use a larger interval. Again, trading out how big the file is for how close it is to real life. The quantizing step always introduces some amount of quantization error, which is measured by comparing the actual signal value with the quantized value at each sampled point. However, some level of quantization is always necessary for storing analog data in digital form due to the finite nature of a computer's memory and its numeric precision. Again, whether we choose to round it at 25 volts or 1 volt or 0.1 volts, at some point we are rounding. And we just get to determine how close our interval is going to be. Okay, so let's take a moment to pause and recap what we just learned. When changing analog data to digital, there are two major problems that we need to deal with. The first is that there are too many points on the curve for our computer to handle. There are infinitely many, in fact, which is guaranteed to create overflow problems. We deal with this with a process called sampling, where essentially we slice the time variable up into equal intervals and take those points as representative of the entire curve. We then ignore the rest of the curve, giving us a manageable number of points to work with. The second problem involves precision. A computer cannot represent irrational y values perfectly, so it needs to round. By setting a quantization interval, we can determine how accurate we want each point to be. The smaller the interval, the more accurate the points. So to get the highest quality sound, both of these intervals should be very small. This will lead to more points that are also more accurate. Of course, the more sample points we take and the more accurate we make them, the more bits that's going to take up and the larger our file is going to be as a result. Unfortunately, we're not quite done yet. The numbers still need to be put into binary, and the computer actually has a couple of tricks that it can use to simplify the numbers so that it takes up less space. Let me show you what I mean. Our final step is called binary encoding, which really just means taking the numbers and putting them into binary. However, like I said a moment ago, there are a few tricks that the computer is going to use to make these numbers simpler and easier to store. If there is a limited set of quantized y values, the computer does not need to store the actual value. Instead, it can store a much smaller value that represents the quantized y value. For this signal, a quantization interval of 25 resulted in 9 possible y values. We can map the 9 values to the binary numbers for 0 through 9. So if you take a look at this graph, this is still the same graph, they are still the same points. The only difference is that the axes have been changed. For one thing, we are now counting from 0 to 9 in binary, and also you'll notice that instead of having 0 on the x-axis in the middle where it normally goes, 0 actually is the very bottom value of those bottom 2 points. And this means we don't have to deal with negative numbers, which again is going to mean that we can use less bits to represent our points. So this point here, the one that's next to V, it used to have XY coordinates of 33, 102, 33 milliseconds, 102 volts. But now that we've got our shape set, we could instead call that point 19, because from the 0, it's over 1 and up 9. That is a much smaller number, it uses up a lot less space, and is still going to give us the same shape once we're done. Don't get too hung up on this particular process. It's just a matter of compressing the file so that it uses fewer bits without getting any more inaccurate than it already was. We can then encode the signal into this binary sequence, and of course, for the computer to understand the sequence, our digitized version would also need to include a description of how the sequence was sampled and encoded. We would have to give the intervals to the other computer as part of the file so that they can decode it and have it come out right. This encoding uses 4 bits per sample. As you can see, 1, 2, 3, 4 bits per sample. The number of bits per sample is also known as the bit depth. The lowest bit depth is 1 because, of course, 1 bit is the smallest you can possibly have, which can only describe 2 values, 0 or 1. The standard bit depth for telephone calls is 8 bits, which is 256 values. Check a previous video if you don't remember how that works. And the recommended bit depth for YouTube music videos is 24 bits, which is over 16 million possible values. Play around again with the quantization interval and observe how the bit depth changes. What intervals only need 2 bits, 4 bits, or 6 bits? So when I make the interval smaller, notice how the number of bits is going up. Now it's taking, looks like 5 bits instead of 4. If I make them as small as it possibly can, it looks like 1, 2, 3, 4, 5, 6, 7 bits. So that graph is going to be very, very accurate, but since each point takes 7 bits and there's a lot more points, that's going to make that a much larger file. It's going to take longer to transfer, it's going to take longer to download. Finally, reconstruction. We often store analog signals in digital storage so that we can reproduce them later, like playing back an audio file, displaying an image, or listening to a YouTube lecture. When a device wants to convert a digitized signal back into an analog signal, it will attempt to reconstruct the original continuous signal. For this signal, a simple reconstruction strategy could interpolate, which just means sort of kind of guesswork, a smooth curve through the quantized points. So as you can see, they took those same points we've been working with the whole time, and it kind of sort of estimated a curve that could go through those points. How well does that match the original? Well, we can overlay the curves to see the difference visually. You see, they're pretty close. They're definitely not perfect, but they're pretty close. If we can decrease the sampling interval and lower the quantization error, we can bring the reconstructed curve closer to the original signal. We could also use different strategies for reconstructing the signal. And remember, the closer those two curves are to each other, the more accurate the sound will be, the more lifelike it will be, the more it will be like it was when it was recorded. Play around with the different sampling rates and quantization intervals. How close can you get to the original curve? Well, I know how to get really far away from the original curve, and that's to take these intervals and make them really big. See how now it's like only got one curve instead of a whole bunch of them? And if I take the quantization interval and go all the way up, now it does not look anything at all the same. So to get as close as possible, we want to take these two and make them as close as possible. As you can see, when we take the two intervals down to the smallest we possibly can, we get two curves that are basically indistinguishable. Okay, so here's a summary. The first step of sampling converted an infinite stream to a finite sequence. In quantization, the values in that sequence were approximated, they were rounded. Finally, the values were encoded into bits for storage on a computing device. At some later point, a device could interpret those bits to attempt a reconstruction of the original infinite stream of continuous values. Whenever we convert analog data into digital data, whether it's audio or visual, our goal is to sample data with enough precision so that we can reconstruct it later at the desired quality level, but not so much that it exceeds our data storage capacity. Landline telephones use relatively low sampling rates and bit depths because the data must travel over telephone lines, whereas movie directors record film at very high sampling rates and bit depths so that they can replay it on giant screens later. That's why something like a phone call or a Zoom call tends to sound like crap, whereas a podcast or a music album sounds great. Find a device near you that converts analog data into digital data. What sort of space constraints does it have for storing or transferring the data? What sort of detail is lost in the digitized version? So I've got my phone here, which has, of course, cameras on the back and the front, and both of those cameras are digital cameras, so they take the sort of infinite, not quite infinite, but they take all of that light that is bouncing off of me and going into the camera, and it samples it, and it approximates it, and then it's going to spit out essentially a mosaic of colored squares that looks enough like me that the human eye can't really tell the difference. Now, I know this is probably the first really big stumbling block that a lot of you are having. This was a much more complex video than we've had up to this point. If you have any questions, go ahead and put them in the comments below and I will do my best to address them. That said, if you click on the link to the article, which I will have put in the description, there is also a question and answer forum here where you can ask questions, get answers. Hopefully they'll be able to help you out if I can't. This is a pretty difficult piece of the topic, so do not feel bad if you're having a hard time with it. Next video, I'm going to go ahead and do a few exercises from Khan Academy so that we can really solidify this. But until then, thank you for watching.